Hey guys, just wanted to say hi and put a name to a face. Hopefully you're all doing well. I have to say I'm doing okay. Things have obviously been crazy, but everybody's healthy at home and no issues with that. I've probably been eating more than I should, but you know how that goes. I would say the upside to having this arrangement, if you want to call it that, is I get to wear comfy clothes every day. So wearing sweats instead of, a shirt and tie or a collared shirt or something like that. But other than that, this is pretty nuts. Been running karate classes from my basement, which is totally ridiculous. You can see behind me, I have like our background. And so we're doing like classes over Zoom and Facebook Live and YouTube playlists. I got like 100 and something YouTube videos at this point. It's insane. But I hope you're all doing well. I just wanted to say hi. If you're having any issues with getting this work done, let me know. Shoot me an email. Just communicate with me. Obviously, things are different for everybody. And I want to make sure that, we're doing everything we can to help you out. We are getting close to the end. We have about, I would say, a week left to go on this unit. We would have been done by now had we been in regular classroom and not doing the review, but we're going to finish and we'll still have plenty of time for the review for the AP test. So I'm not terribly concerned. I think you guys are in good shape. I am going to start to institute AP Classroom back into the fold. So you'll see that, but not today, but you'll see some posts about that in the coming days. So look for that. And I'm also going to put up some optional practice stuff. I already started doing this, but just so you know, if you want to get the most practice for the AP test and you have the time to do it, I definitely recommend that you do the optional work, but it's not required for you to do. I know that everybody, like I said, everybody's situation is different. And so, we'll go case by case. All right, so the first thing that I wanted to talk about with you today is this thing we call the parallel axis theorem. I alluded to this a little bit, not by name, but in a previous lesson. And the idea here is, you can see what it says in the notes here. In the previous examples, the axis of rotation coincided with the axis of symmetry of the object. So in other words, when we were looking at finding the moment of inertia of the objects like the sphere or the cylinder or whatever, the majority of the time, the axis was right through the symmetrical axis of the object, like its geometric axis. That doesn't have to be the case. So, for example, suppose you have an object that you could model as a thin rod, so like a pencil is a good example. Okay, if we look on our equation sheet, there's an equation that describes the moment of inertia of a pencil about its center axis like this. So if you tried to spin it back and forth like this. All right, and the equation for that is 1/12 ml squared. This is what the parallel axis theorem says. It says for any axis, an arbitrary axis, the parallel axis theorem simplifies calculations, and it says that the moment of inertia equals the moment of inertia about the center of mass plus md squared. And if you look in the notes here, what it says is ICM is about the axis through the center of mass, and the d is the distance from the center of mass axis to the arbitrary axis. So for example, going back to this, if I have my pencil and I spin it back and forth like this, like that's pretty easy. If I move the axis out to the end and I try to spin it from here, that's not as easy to do. Its moment of inertia is not the same because I changed the spot where the axis is. So the parallel axis theorem allows me to figure out what the moment of inertia is about any point if I already know what the moment of inertia is about that center of mass axis. And this is how we do it. So Obviously, it tells us how to do the calculation, but think about this in terms of just a conceptual point. And I'm going to try to use my pen here. This is new. So I want you to pay attention to this right here. The mass times d squared. So basically what we're saying here is that if you're away from the center of mass axis, you have to add this to get the moment of inertia. So that means that the center of mass axis is the least possible inertia. So if you want to orient an object in such a way that it has the least moment of inertia, you want to put the axis right where the center of mass of that object is. All right, so you know me and my martial arts examples. This is the example that comes to my head. I don't know why, but it's kind of ridiculous, but it works. So I want you to imagine swinging something like a sword versus swinging something like an axe. Okay, if you think about it, like an axe has most of its weight at the end in the head, but you're holding it down on the other end. So if you think about like where the axis is, that's where your hands are, that's where it's rotating from, compared to where most of the mass is, okay? The center of mass of that system is far away. The moment of inertia of that is huge. It's going to be really hard to rotate that object. On the other hand, with something like a sword, it's balanced in such a way that there's more weight in the handle than there is in the blade side. So even though the blade is longer than the handle, it's more proportionally balanced so that your hands are pretty close to the center of mass axis. So the moment of inertia of that sword is a lot less. It's easier to rotate that sword than it is to rotate an axe. So that's my silly example, but it works. Okay, so I want to take a look here at, here's an example for the rod that they actually worked out here for you. So the moment of inertia of the rod about its center is 1/12 ml squared. We have that equation in the book. If we move the axis to the end of the rod, the distance would be half the length of the rod. So using the parallel axis theorem here, we would put in half the length of the rod for d. So that goes here. And we add the moment of inertia about the center of mass to this md squared term, d being L over 2. And once you reduce that, you end up with this. And this equation is actually already in the book. But this came from using the parallel axis theorem. All right, so that's an important point. And like I said, you know, going back to the conceptual point, moment of inertia is always going to be lowest when you're closest to the center of mass axis. The closer you get, the more, the less inertia you're going to have. If you remember, we did that one problem about a week ago, maybe a little more, with the frame where we had 4 masses in the corners. And I was saying to you that when the mass is closer to the center of mass, or when the axis is closer to the center of mass, that you're going to get a lower rotational inertia. And that problem definitely also demonstrated that point. Okay, now I want to go to talking about torque. Okay, so I want you to think back to when we learned about Newton's laws. What we learned is that a force is required to change an object's motion. Or another way of saying that is that a force is required for an object to accelerate. And the first law tells us that, but the second law really describes quantitatively how it works. So the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to the mass. So we saw plenty of examples of this. When you increase the net force on an object, you're going to increase its acceleration. But if you increase the mass of the object, you're going to decrease the acceleration because more mass is more difficult to accelerate. Okay. In the book, they go through the proof of this. It's not a proof that you need to know how to do. But what we can prove is that torque is required to change an object's rotational motion. So in a very similar fashion, if we want to change an object's rotational motion, have angular acceleration that is, then we need a torque. And the more torque we have, the more angular acceleration we're going to get. And the more rotational inertia an object has, the less acceleration we're going to get. So this, guys, is Newton's second law in rotational form. So we'll call it Newton's second law for rotation. All right, it basically says the same thing as this. We have acceleration here. We have acceleration here. This is just an angular acceleration. We have net force up here. Instead of force, we have torque here because a torque is a force that causes rotation. And then instead of mass, we have the rotational inertia. Remember, mass is a measurement of inertia in a linear sense. Rotational inertia is the inertia of an object in a rotational sense. Okay. So what I wrote here to kind of finish it up. More torque produces more angular acceleration, and more rotational inertia produces less angular acceleration. This is Newton's second law for rotation. All right, so we're going to start to look at examples of this, and both conceptual and quantitative. All right, so the first one I have is something that you may have thought about already. Think about a person who walks on a tightrope. Many times when you see somebody walking on a tightrope, you'll see them carrying this long and heavy pole. I had an opportunity, I don't know if any of you had the opportunity to do this, it's pretty neat. A couple years ago, the Franklin Institute had an exhibit about circus science. And they had one of these poles that the tightrope walkers use there, so you could like actually feel what that felt like and how long it was and how heavy it was. I knew they were heavy, but I didn't know how heavy until I actually did it. So that was pretty neat. Think about why they do this. Why do they use this pole? Well, because it increases their rotational inertia, right? If you're walking on a tightrope, you don't want to rotate. Think about it. The person's foot, let's say right here, is the axis. All right, if they start rotating around that axis, they're going to fall off the tightrope, all right, which would be obviously possibly fatal. All right, so they don't want to rotate, so they want to do everything they can to increase their inertia so that it's harder for them to rotate. So by using this heavy, long pole, they're moving a lot of mass way out here and over here like this. All right, so there's a lot of mass far away from this axis that we talked about. And by doing that, they're increasing their inertia, so it's harder for them to tip over. Right, but there's another part to this too. If you go back and look at what we said in the last slide, increasing the inertia decreases the angular acceleration. So suppose they are doing the tightrope and they make a bad step. All right, so you know they're now off balance. By having this pole, the rate at which they start rotating over is going to be reduced. So if they start to tip, it's going to happen more gradually. So they have more time to kind of readjust their balance and make things a little bit easier for them to stay on a tightrope. Right? And think about this too. If you've ever, you know, and I'm sure you have, but if you've ever been walking or whatever and you've lost your balance before, one of the first things you do when you lose your balance is you kind of stick your arms out like this. If you ever stopped and think about why this happens naturally, you're basically trying to do what the tightrope walker is doing with the pole. All right, your brain knows subconsciously that by putting your arms out like this, you are harder to fall over. It's more difficult for you to tip. All right, and this is a consequence of everything we've talked about with moment of inertia and with, you know, now Newton's second law of rotation. Okay, so we're going to do one example problem, and it's in your book. It's on page 224 of the textbook, and it's example 812. So I'm going to bring that up here. Okay, so here's what it says. A 15 Newton force is applied to a cord wrapped around a pulley of mass 4 kilograms and radius 33 centimeters in the figure. The pulley is observed to accelerate uniformly from rest to reach an angular speed of 30 radians per second in 3 seconds. If there is a frictional torque at the axle of 1.1 Newton meters, determine the moment of inertia of the pulley. The pulley is assumed to rotate about its center. Okay, so here's some of the information. I didn't put everything in, but here's some of the information that we were given. The force that's being applied to the pulley is 15 newtons. There's also a frictional torque that they gave us. The radius is 33 centimeters, that's 0.33 meters. And the mass of this thing is 4 kilograms. Okay, so let's take a look at what else they told us. They also told us that it's accelerating from rest to 30 radians per second in 3 seconds. Okay, so let's write that down here. What we have is it started from rest and it got up to 30 radians per second in 3 seconds. Okay, so we can use this information here. This is telling us about how the rotational motion is changing. So we can use this information to figure out the angular acceleration. You could probably do it in your head, but we're going to do change in omega over t to find the acceleration. So omega final minus omega initial over t. It's still weird getting used to this tablet because I have to look at the screen to write. I can't look at what I'm writing. I can't look down at what I'm writing. All right, so I have 30 radians per second minus 0 over 3 seconds. So we get 10 radians per second squared. Okay. Now, we know what this is. If we can find the net torque, we could use Newton's second law for rotation to find the moment of inertia of this pulley. All right, so take a look. Here's what we know. There's a frictional torque opposing the rotation of 1.1 Newton meters, and then there's this force that's causing it to rotate counterclockwise. So let's figure out the torque from that. So that force is being applied right here. If we find the torque from that force, let's call it the torque applied. It's going to be the 15 Newton force times the distance from the axis, which is 0.33 meters. And if we draw a line, we use a different color here, from the axis to where the force is being applied, apologize for my not straight line, that makes a 90-degree angle with this force. So it's times sine of 90. Sine of 90 is 1. I'm not going to write it down. We just have 15 times 0.33. So let's do that in the calculator. Well, we need a calculator. 15 times a third is 5, right? We don't need a calculator. We have 5 Newton meters. Okay, so we have this applied torque of 5 Newton meters. We have this frictional torque going against it of 1.1 Newton meters. So the net torque is going to be the 5 minus the 1.1, which is going to be 3.9 Newton meters. Okay, so we have the net torque. We have the angular acceleration. We can use the two of them together to find the moment of inertia. So Newton's second law for rotation says that the angular acceleration is equal to net torque divided by I. And we want to know I. So replace I on this side and move alpha to this side. So we're going to get I equals the net torque, which is 3.9, divided by the angular acceleration, which was 10 radians per second squared. We're going to get 0.39. And the units here are kilogram meters squared. If you're not seeing where that came from, just think about going back and breaking out what a Newton is: kilogram meter per second squared times meters. Radian's not a unit, so this is really 1/second squared. So reduce it all down, you should get this. So I'm going to ask you to do some problems that are kind of similar, and hopefully you'll be able to follow right along with that and take it from there. All right, it was good seeing you guys. Oh, good saying hi to you guys. I can't see you. But, and I'll talk to you soon. Let me know if you have any questions about this video by putting them in the comments to my post on Google Classroom.